Hello, everyone. Thank you for coming. Let's continue. Earth. In the previous presentation 6, we discussed different aspects of the Earth, a condition of early Earth before the beginning of life on it, internal structure, the 660 kilometers boundary that we named geomagma with electrical conductivity, random variations of Earth's rotational speed on daily basis, origin of moon, expanding Earth, internal heating, faint young sun paradox, geocorona, and planetary coronas. Our model revealed the fact that the sun and the moon activity causes the geomagma activity, and as a consequence, random variations of Earth's rotational speed by the periodically varying sun's and moon's magnetic field. Today, we will discuss Earth's high-energy atmospheric physics. In his The Mystery of Lightning review, leading lightning physicist Joseph Dwyer provides an excellent overview of the main experimental observations and leading models of thunderstorms and lightnings. Many mysteries remain about how thunderstorms and lightnings work, including how lightnings get started. It is established that thunderstorms and lightnings produce intense bursts of X-rays and gamma rays. This high-energy radiation may be important for understanding how lightning works. In this presentation, we give an explanation for high-energy atmospheric phenomena through the frames of Hypersphere World-Universe Model, in whom terrestrial gamma ray flashes are in fact gamma ray bursts. The spectra of TGFs at very high energies are explained by universe-created particles self-annihilation in geocorona. Lightning initiation problem is solved by gamma ray bursts, which slam into thunderclouds and carve a conductive path through a thunderstorm. High-energy atmospheric physics. Lightning initiation problem. Years of balloon, aircraft, and rocket observations have never found large enough electrical fields inside thunderstorms to make a spark. And yet lightning strikes the Earth about 4 million times per day. This has led to the cosmic ray model of lightning initiation. Cosmic ray slams into atmosphere and carves a conductive path through a thunderstorm. Air showers alone will not increase the conductivity enough to initiate lightning. A mechanism of runaway electron avalanche was proposed by Gurevich et al. In 1992 in order to increase ionization. Strong electric fields accelerate electrons to nearly the speed of light. These electrons emit X-rays and gamma rays, which were observed by Fishman et al. In 1994. A gamma ray flash descends from the overhead thundercloud. It is not clear why some discharges make X-rays and others do not. Gamma rays are produced inside of thunderstorms. Explosive production of energetic particles were observed from space by Fishman et al. Thunderstorms create electron and positron beams. Thunderstorms produce terrestrial gamma ray flashes. Terrestrial gamma ray flashes were first detected by chance by NASA's Earth-orbiting Compton Gamma Ray Telescope. Compton was searching for gamma ray bursts from exploding stars when it unexpectedly began detecting very strong bursts of high-energy X-rays and gamma rays coming from Earth. Detectors observed an unexplained terrestrial phenomenon, brief, lasting about a millisecond, intense flashes of gamma rays. According to Fishman, these flashes must originate in the atmosphere at altitudes above at least 30 kilometers in order to escape atmospheric absorption and reach the orbiting detectors. The photon spectra from the events are very hard, peaking in the high energy portion of the spectrum, and are consistent with Bremsstrahlung emission from energetic mega electron waltz electrons. The most likely origin of these high energy electrons, also speculative at that time, is a rare type of high altitude electrical discharge above thunderstorm regions. An article, Properties of the 100 thundercloud discharges responsible for terrestrial gamma ray flashes, Dwyer in 2013 provides a brief review of TGFs. They have durations ranging from a few tenths of microseconds to a few milliseconds and produce the highest energy emission of natural phenomena originating from within the Earth's atmosphere. TGFs are relatively common, with thousands or more produced around the planet each day. Spacecraft measurements have found that the source altitudes of the gamma rays must be below 20 kilometers, within the altitude range of thunderstorms. The spectra of TGFs, up to a few tenths of megaelectron volts, are consistent with Bremsstrahlung emissions from energetic electrons accelerated by strong electric fields within the thunderclouds, although there is currently some debate about the spectra at very high energies, about 100 megaelectron volts. It is a challenge to develop models that can explain how large numbers of high-energy electrons are generated so rapidly deep within the atmosphere. According to Dwyer, there are two leading models of TGF formation. Lightning leader emission, similar to X-ray emission seen near the ground. Dark lightning, which generates so many high-energy particles that it discharges the thunderstorm faster than normal lightning, makes currents over 100,000 amps, emits very little visible light that appears dark, can explain terrestrial gamma ray flashes. Cosmic rays are not needed. But how can we explain a new mystery? A bright TGF was seen by spacecraft in the middle of Sahara Desert on a nice day. The nearest thunderstorms was about 1,000 miles away. Let's summarize obtained results, which are difficult to explain in frames of the existing models. Sometimes ball lightnings appear without apparent connection to a lightning bolt. Unusual surges of radiation at 511 kiloelectron volts when there were no thunderstorms. Beams of antimatter positrons produced above thunderstorms on Earth. A gamma ray flash coming down from the overhead thundercloud. Some discharges make X-rays and others do not. Explosive production of energetic particles observed from space. Thunderstorms make electron and positron beams. Thunderstorms produce TGFs. A bright TGF was seen by spacecraft in the middle of Sahara Desert on a nice day. The spectra of TGFs at very high energy, 100 megaelectron volt. Geocorona is the luminous part of the outmost region of the Earth's atmosphere. It extends to at least 640,000 kilometers from the Earth. X-ray from Earth's geocorona in the range of energies 0.0810 kiloelectron volts were first detected in 1999. The main mechanism explaining the geocorona X-rays is that they are caused by collisions between neutral atoms in the geocorona with carbon, oxygen, and nitrogen ions in the solar wind. This process is called charge exchange, since an electron is exchanged between neutral atoms in geocorona and ions in the solar wind. Warm explanation. The characteristics of geocorona are similar to the characteristics of the solar corona. We discussed it in the presentation 6. The geocorona, made up of universe-created particles, resembles a honeycombed field with plasma, including the ionosphere from about 60 kilometers to 1,000 kilometers altitude. The geocorona, composed of UC fermions UCF1, UCF2, UCF3, has the size that is much larger than the size of the Earth. At the distance of 640,000 kilometers from the Earth, atoms and molecules are so far apart that the outmost region of the Earth's atmosphere no longer behaves like a gas. As the result of large fluctuation of UC particles in geocorona and their cell annihilation, X-rays and gamma rays are going not only up and out of the Earth, but also down to the Earth's surface. In case they were produced at altitudes of above at least 30 kilometers, they can reach the orbiting detectors. In case the source altitudes of the gamma rays is below about 20 kilometers, within the altitude range of thunderstorms, they can reach the surface of the Earth. TGFs are, in fact, well-known gamma ray bursts. X-rays and gamma rays are the consequence of UCF1 and UCF2 and UCF3 self-annihilation. The spectra of TGFs at very high energies can be explained by UCF1 and UCF2 self-annihilation. Lightning initiation problem can be solved by X-rays and gamma rays, which slam into the thunder clouds and carve a conductive path through a thunderstorm. From this point of view, it is easy to explain all experimental results summarized above. Ball lightning. Ball lightning is unexplained atmospheric phenomenon that is usually associated with thunderstorms and lasts considerably longer than the split-second flash of a lightning bolt. Ball lightning usually appears during thunderstorms, sometimes within a few seconds of lightning, but sometimes without apparent connection to a lightning bolt. In some cases, ball lightning appears after a thunderstorm or even before it. In 1972, Chairman published a review in which he identified the properties of a typical ball lightning. They frequently appear almost simultaneously with cloud-to-ground lightning discharge. They are generally spherical or pear-shaped with fuzzy edges. Their diameters range from 1 centimeter to several meters, most commonly 10-20 centimeters. They can be seen clearly in daylight. The lifetime of each event is from 1 second to over a minute, with the brightness remaining fairly constant during that time. They tend to move most often in horizontal direction at a few meters per second, but may also move vertically, remain stationary, or wander erratically. Many of them are described as having rotational motion. It is rare the observers report the sensation of heat, although in some cases the disappearance of the ball is accompanied by the liberation of heat. Some display an affinity for metal objects and may move along conductors such as wires. Some appear within buildings, passing through closed doors and windows. Some have appeared within metal aircraft and have entered the and left without causing damage. The disappearance of ball is generally rapid and maybe either silent or explosive. So many variations. Short history of ball lightning hypothesis. Different hypotheses were proposed to explain ball lightnings, but no one explanation is widely accepted at present. Vacuum hypothesis by Nikola Tesla, 1904. Microwave cavity hypothesis by Peter Kapitsa. Antimatter hypothesis by David Ashby and Colin Whitehead. Meso-solid tone hypothesis by Peter Handel. Black hole hypothesis by Mario Rabinovich. Microwave bubble hypothesis by Wu. Extreme ball lightning hypothesis. Van de Vender in 2011 distinguished extreme ball lightning from ordinary ball lightning by the following characteristics. It glows in air. It originates from nothing visible. It lasts between 10 and 1200 seconds. It is lethal or potentially lethal. It causes significant damage. It contains energy estimated at 100,000 to 1 billion joules, far in excess of the energy density attributable to chemicals or electrostatics. It penetrates walls, glass, and metal, generally without leaving a hole. It leaves black streaks on corpse without the spasm of electrocution. It can excavate tons of earth. Extreme ball lightning in County Donegal, Ireland on August 6, 1868 traveled about 1.6 kilometers and excavated about 200 cubic meters of water-saturated pit in about 1200 seconds. Van de Vender followed up a reputable report by Michael Fitzgerald to the Royal Society with a visit to the site. He confirmed the essentials as far as it was possible so long after the event. It was evident that the conductive pit would immediately neutralize any charge, so extreme ball lightning cannot be electrostatic. According to Van de Vender, to date, no theory addresses the characteristics of extreme ball lightning. He said it seems to require new physics. In view of Thornhill in 2006, explaining extreme ball lightning does not require new physics. The clue of his hypothesis comes from the observed ability of extreme ball lightning to penetrate solid material. According to Thornhill, there is one stable particle that has the ability to pass through solids without any appreciable effect, neutrino, which in the presence of the excited nucleus may accept a lower level of energy than required for pair production and form a stable heavy neutrino. There is only one defect of this hypothesis. Neutrinos have no energy at all. Observations of characteristics of ball lightning. One particular large example was reported on the authority of Dr. Gregory in 1749. Admiral Chambers, on board of Montague for November 1749, was taking an observation just before noon. He observed a large ball of blue fire about 3 miles distant from them. They immediately lowered their topsails, but it came up so fast upon them that before they could raise the main tack, they observed the ball rise almost perpendicularly and not above 40 or 50 yards from the main chains when it went off with an explosion as great as if 100 cannons had been discharged at the same time, leaving behind it a strong sulfurous smell. By this explosion, the main topmast was shattered into pieces, and the main mast went down to the keel. 5 men were knocked down, and one of them were bruised. Just before the explosion, the ball seemed to be the size of a large millstone. Observations of the optical and spectral characteristics of ball lightning was made by Sen et al. In 2014. At a distance of 900 meters, a total of 1.64 seconds of digital video of the ball lightning and its spectrum was obtained. From the formation of the ball lightning after the ordinary lightning struck the ground up to the optical decay of the phenomenon. The ball lightning traveled horizontally across the video frame at an average speed of 8.6 meters per second. It had a diameter of 5 meters. Oscillations in the light intensity and in the oxygen and nitrogen emission at a frequency of 100 Hz, possibly caused by the electromagnetic field of the 50 Hz high voltage power transmission line in the vicinity, were observed. From the spectrum, the temperature of the ball lightning was assessed as being lower than the temperature of the parent lightning, less than 15-30,000 Kelvin. The observed data are consistent with vaporization of soil as well as with ball lightning sensitivity to electric fields. Nikitin et al. In 2023, in the article Explosions of Ball Lightnings Inside Enclosed Spaces, estimated the value of energy density of lightly or highly energetic ball lightning, it's about 10 to the power 10 joule per cubic meter, and the energy of the explosion of this ball lightning to be equal to 130 megajoules. These estimations allowed the authors to say that ball lightning is a dangerous natural phenomenon. On figure 1, we can see the result, the house wall thrown out by this explosion. You see there is only wall and there is no any other residual stones and some other particles. There is only explosion. According to Oreshka in 2012, Kapisa supposed that a ball lightning is a window in another world. We analyzed the possibility of existence of other worlds, micro world, small world, and large world, based on the proposed weak, super weak, and extremely weak interaction, respectively. It was suggested that ball lightning is an object of the small world. Macro world, in whom strength of gravity is characterized by gravitational parameter g, where g0 has the fixed expression, is an extrapolated value of g at the beginning of the world. T is the gravitodynamic constant, H is the Planck constant, and A is a basic size unit about 10 to the minus 14 meters. Dimensionless time-varying quantity Q is a measure of the age of the world that equals tau over T0, where tau is the cosmological time and basic time unit T0 equals to about 10 to the minus 23 seconds. In the present epoch, Q equals about 10 to the power 14. The range of gravity equals to the size of the world, about 10 to the power 26 meters. Bohm foresees the 3 additional types of interactions between universe-created particles, weak, super weak, and extremely weak, characterized by the following parameters respectively. In our view, each type of UC particles interactions provides integrity of the corresponding world. Microworld. is characterized by the parameter g weak, which is about 30 orders of magnitude greater than g. The range of the weak interaction for USC particles with Compton length LUCP in the present epoch equals to this equation. For example, particles UC fermion UCF1 with the rest energy 1.3 tera-electron volts, where alpha is a dimensionless Rydberg constant and the basic energy unit E0 equals to 70 mega-electron volts, have Compton lengths about 10 to the minus 18 meters, and the range of the weak interaction about 10 to the minus 8 meters. That is much greater than the range of the weak nuclear force. It's about 10 to the minus 16, minus 70 meters. Small world is characterized by the parameter G super weak, which is about 20 orders of magnitude greater than G. The range of the super weak interaction for the particle UCF1 equals to 82.2 meters. In whom ball lightnings are macro objects which have cause made up of weakly interacting particles UCF1 surrounded by shells composed of the electron-positron plasma contaminated by chemical elements of soil and air as the result of TGF strike of the ground. Super weak interaction between particles UCF1 and all particles around the core provides integrity of ball lightnings. Large world is characterized by a parameter G extremely weak, which is about 10 orders of magnitude greater than G. The range of the extremely weak interaction in the present epoch equal to this equation, that it equals to 1.5 light years or about 96,000 astronomical units. In our view, extrasolar systems are large world objects. Extremely weak interaction between universe-created matter cores and all particles around them provides extrasolar systems integrity. Ball lightning formation. The clue of our model comes from the observed ability of ball lightnings to penetrate solid materials. It means that the core of ball lightning should be composed of UC particles. Following Tesla vacuum hypothesis, we suppose that when sudden and very powerful TGF passes through the air and strikes the surface of the Earth, the tremendous expansion of some portions of the air and subsequent rapid cooling and condensation gives rise to the creation of partial vacua in the places of greatest development of heat. These vacuous spaces, owing to the properties of the gas, are most likely to assume the shape of hollow spheres when, upon cooling, the air from all around rushes in to fill the cavity created by the explosive dilatation and subsequent contraction. In whom the places of greatest development of heat are the spots on the Earth's surface struck by TGF. As a result, the ablation of the soil takes place, and vaporized chemical elements of soil and the oxygen and nitrogen from the air can be absorbed by ball lightnings and observed experimentally. Very powerful gamma quants with energy at least 1 megaelectron volts in the vicinity of atomic nuclei of the ground can produce electron-positron pairs with high concentration. This collisionless, unmagnetized electron-positron plasma, whose properties are very well studied, composes a shell around UC matter core of ball lightning made up of UC fermion 1 and provides the affinity for metal objects such as wires. The most important part of the ball lightning formation is UC matter core. The calculated density of geocorona composed of particles UCF1 near the surface of the Earth is about 10 to the minus 7 kilogram per cubic meters. Let us calculate a radius of sphere in geocorona having mass about Planck mass. It's about 0.275 meters. That is a reasonable size of geocorona bubble. UCM core of the ball lightning has a maximum energy in accordance with plus Planck mass about 10 to the power 9 joules. That corresponds to the estimated by one Devender value 10 to the power 5, 10 to the power 9 joules, and by Nikitin et al. 130 megajoules. In accordance with vacuum hypothesis by Nikola Tesla, when powerful TGF strikes the surface of the Earth, the explosive dilatation of the portion of geocorona with radius RGC gives rise to the creation of hollow sphere with partial vacuum and all UC particles outside of the sphere. The subsequent rapid contraction induces UC particles rush in to fill the cavity. As a result, at the center of the sphere arises micro-objects with mass about Planck mass and density high enough for the beginning of the UC particles self-annihilation. According to whom, all gravitationally rounded macro objects in hydrostatic equilibrium down to the moon of the Saturn Mimas have UCM reactors inside of them. Considering that the mean density of the Mimas is about 115,000 kilogram per cubic meter, with UCM core made up of self-annihilating UCF1, we can estimate an average density of the core about 1,000 kilogram per cubic meters as the minimum density for the effective self-annihilation. Then the size of the core is about 10 to the minus 4 meters. Mass of the small ball lightnings is mostly in the UCM cores. Then they can easily penetrate through walls, glasses, metals without leaving a hole. Considering the density of the atmosphere about 1.25 kilogram per cubic meter, we can calculate the minimum radius of the ball lightning corresponding to the core's mass only 0.16 centimeters. That is in a good agreement with experimentally observed value of ball lightning minimum size about 1 centimeter. We take density of the atmosphere for the average ball lightning density to explain movement of ball lightning in air. Practically all mass of extreme ball lightnings is in electron-positron plasma. Extreme ball lightning with diameter 5 meters observed by Sen et al. In 2014 had a mass of about 82 kilograms. As the conclusion, ball lightning belongs to the small world. Ball lightning has the core made up of UCF1 surrounded by the electron-positron plasma contaminated by chemical elements of soil and air as the result of TGF strike of the ground. The core of ball lightning irradiates quants with different energies and attracts new UC particles from geocorona due to super weak interaction. It explains the observed result that the brightness of ball lightning remains fairly constant during its lifetime. UC particles supply not only additional mass, but also additional angular momentum. It explains the fact that many of ball lightnings are described as having rotational motion. Tunguska Event observations. On June 13, 1908, at around 7:17 a.m. local time, Evenki natives and Russian settlers in the hills northwest of Lake Baikal observed a bluish light nearly as bright as the sun, moving across the sky and leaving a thin trail. About 10 minutes later, there was a sound similar to artillery fire. The explosion registered at seismic stations across Eurasia, and airways from the blast were detected in Germany, Denmark, Croatia, and the United Kingdom, and as far away as Batavia, Dutch East Indies, and Washington, D.C. It is estimated that in some places the resulting shock wave was equivalent to an earthquake measuring 5.0 on the Richter magnitude scale. Description: Tunguska Event was an explosion estimated to have a yield of at least 330 megaton of trinitrotoluol. The explosion is generally attributed to a meteor burst, atmospheric explosion of stony asteroid about 50-60 meters in size. The asteroid approached probably with a relatively high speed of about 27 kilometers per second. Though it is classified as an impact event, the object is thought to have exploded at an altitude of 5 to 10 kilometers rather than having hit the Earth's surface, leaving no impact crater. There have been about 1,000 scholarly papers, most in Russian, published about the Tunguska explosion. It's very important that there was no impact crater. Meteor airburst is a type of airburst in which a meteoroid explodes after entering a planetary body's atmosphere. This fate leads them to be called fireballs or bolides, with the brightest airbursts known as superbolides. Such meteorites were originally asteroids and comets of a few to several tens of meters in diameter. A bolide is a fireball reaching an apparent magnitude of minus 14 or bright, more than twice as bright as the full moon. A superbolide is a bolide that reaches an apparent magnitude of minus 70 or bright, which is roughly 100 times brighter than the full moon. Recent examples of superbolides include the Satas Mill meteorite in California, an energy yield of about 4 kiloton of TNT, the Chelyabinsk meteor in Russia, the explosive energy 460-470 kiloton of TNT, and the Kamchatka meteor in Russia, which was an asteroid roughly 10 meters in diameter, entered the atmosphere at a speed of 32 kilometers per second, with a TNT equivalent energy of 173 kiloton. This energy was more than 10 times the energy of the little boy bomb dropped on Hiroshima in 1945. Early estimates of the energy of Tunguska airburst ranged from 10-15 megaton to 30 megaton of TNT, depending on the exact height of the burst as estimated when scaling laws from the effects of nuclear weapons are employed. The 15 megaton estimate represents an energy about 1,000 times greater than that of Little Bomb. It equals to that of the United States Castle Bravo nuclear test in 1954 and one-third that of the Soviet Union's Tsar Bomba test in 1961. UC government census reported 971 entries of fireballs from May 1988 to December 2023. It's a pretty usual phenomenon. Earth impact model. Meteorites enter the Earth's atmosphere from outer space, traveling at speeds of at least 11 kilometers per second, and often much faster. Despite moving through the rarefied upper reaches of the Earth's atmosphere, the immense speed at which a meteor travels rapidly compresses the air in its path. The meteoroid then experiences what is known as ram pressure. As the air in front of the meteoroid is compressed, its temperature quickly rises. This is not due to friction, rather, it is an adiabatic process, a consequence of many molecules and atoms being forced to occupy a smaller space. Ram pressure and the very high temperatures it causes are the reasons few meteors make it all the way to the ground. Most simply burn up or are ablated into tiny fragments. Larger or more solid meteorites may explode instead. As theorized by Cooper in 1951, a disk-like belt of icy bodies exists beyond Neptune. These icy objects, occasionally pushed by gravity into orbits, bringing them closer to the Sun, become the so-called short-period comets with less than 200 years to orbit the Sun. A comet is an icy, small solar system body with nuclei composed of loose collections of ice, dust, and small rocky particles. There are two main classes of comets: short period comets, called ecliptic comets, and long period comets, called isotropic comets. Ecliptic comets have relatively small orbits below 10 astronomical units and follow the ecliptic plane, the same plane in which the planets lie. All long period comets have very large orbits, thousands of astronomical units, and appear from every direction in the sky. How and when comets formed is debated, with distinct implications on for solar system formation, dynamics, and geology. An asteroid is a minor planet, an object that is neither a true planet nor a comet, that orbits within the inner solar system between the orbits of Mars and Jupiter. They are rocky, metallic, or icy bodies. Sizes and shapes of asteroids vary significantly, ranging from 1 meter rocks to a dwarf planet almost 1,000 kilometers in diameter. The total mass of the asteroid belt is about 3% that of the Moon. Warm explanation. Main results of meteor airbursts are: they are a type of airburst in which a meteoroid explodes after entering a planetary body's atmosphere. This fate leads them to be called fireballs or bolides, with the brightest airbursts known as superbolides. Comets are leftovers from the dawn of solar system around 4.6 billion years ago and consist mostly of ice coated with dark organic material. They have been referred to as dirty snowballs. How and when comets formed is debated, with distinct implication for solar system formation. Asteroids and comets formation. In frames of womb, ecliptic comets were produced by the Sun itself as the result of volcanic rotational fission of the Sun's UC matter core 4.57 billion years ago. Nearly isotropic comets were produced by giant planets with different directions of their rotational axis, which are in fact failed stars as the result of the rotational fission of their UC matter cores. In our view, random explosive volcanic rotational fission of the Sun's UC matter core looks like a firework of UC matter cores of satellite objects at the same time, so that the direction of the sun or the satellite's angular momentum coincides with an angular momentum of the sun. There are no preferences of directions of satellites versus random rotation direction. UCMAC course of satellite objects can be any size from 1 meter to thousands of kilometers. Satellites are rocky, metallic, or icy bodies as the result of the self-annihilation of UC particles inside of their cores, encased when a density of cores more than 1,000 kilogram per cubic meter. That is enough for the efficient self-annihilation. All compositions of asteroids and comets are homemade. Formation of all objects in solar system has a good explanation. Tunguska superbolide. In case when the density of UCM cores of satellite is less than 1,000 kilogram per cubic meter, the self-annihilation process is not efficient. Then there is a possibility of stable UCM metabolites, which are the analog of extreme ball lightnings with much larger internal energy. The range of weak interaction for particles UCF1 is about 10 to the minus 8 meters. We calculated it before. And the calculated minimum particles concentration, about 10 to the power 24 per cubic meter. Considering the rest energy of UCF1, 1.3 tera electron volt, we can calculate the minimum energy density of UCM core, about 10 to the power 17 joule per cubic meter. That is equivalent to the mass density of 3.44 kilogram per cubic meter. That is not enough for the efficient self-annihilation. Tunguska superbolide has the calculated maximum energy about 10 to the power 17 joules. It means that a maximum of its UCM core volume is about only 0.4 cubic meters. The calculated maximum diameter of the superbolide is 482.2 meters. We calculated it before. In our view, weak interaction of particles UCF1 provides the integrity of the superbolide's core and super weak interaction of the superbolide itself. Tunguska superbolide is a stable macro object before entering the Earth's atmosphere. Superbolide entered the Earth's atmosphere from outer space, traveling at speed of 27 kilometers per second. Despite moving through the rarefied Earth's atmosphere, the immense speed at which it traveled rapidly compressed the air in its path. The superbolide then experienced ram pressure. As the air in front of it is compressed, its temperature quickly rises. Ram pressure and the very high temperatures caused increasing of the UCM core's energy density up to the critical value of 1,000 kilogram per cubic meter, when the efficient self-annihilation of particles UCF1 took place and UCM matter core exploded. Conclusion. It is important to emphasize that the initial energy required for a extreme ball creation is insufficient for its sustenance of up to 1200 seconds. Additional energy, therefore, must be consumed by extreme ball lightning once it had been formed. Wurm predicts a new phenomenon, a generation of ball lightnings according to the proposed model of them. Once we master the creation of ball lightnings and extreme ball lightnings in a controlled environment, we can concentrate our efforts on harvesting that energy from a practically infinite source, the medium of the world with you see particles. World-Universe Model can serve as a basis for high-energy atmospheric physics. Acknowledgements. As usual, I am always grateful to academician Prokhorov and Professor Manenko, whose influence on my scientific life has been decisive. I am eternally grateful to my scientific father, Paul Dirac, who was a genius and foresaw the future of physics in a new cosmology. I am forever grateful to Nikola Tesla, who was a genius. I am much obliged to Professor Gordon for publishing my manuscript in the Journal of High Energy Physics, Gravitation, and Cosmology. I am grateful to Nick Percival and Harry Ricker for valuable comments and suggestions, which have led to an overall improvement of the presentation. Special thanks to my son Ilya, who helped me clarify, model, and improve its understanding. This is the end of the presentation. Thank you so much for your attention.